报名听个 presentation 呢？啊？没有，然后你就上长裤了。
帮你们看酷的会穿。没有，没有人讲，他穿长裤不穿我。心情哦。
OK。
比方我就穿长裤，会。看你要搞，哪个是好？你去哪里看来？你头发是不是？好，我给你们拿一个什么？上天是不。
如果
反正不明我在线，然后觉得你在那边有关。
Okay, I think we should start today. So we will do a few examples on change of variable today, and then we will go into vector calculus in the second hour. And next week, Wednesday, quiz from 9 o'clock to Thursday, 5 o'clock. Okay, so I think you should have plenty of time. Huh? Give you more time. Okay, more than one day. Because we cannot put on Thursday, right? Holiday, so drag on. Okay. Yeah. So spend your time, understand the question. Don't just do it for yeah. Huh? Other lecture. I don't know. I also haven't seen it. Maybe next week let you know again. Okay. Let's remind ourselves what's the change of variable. Okay. So suppose we have a 1-to-1 transformation. Okay, T. Let's talk about the case of R3. Okay, R2 you just reduce one variable. Okay, so 1-to-1 transformation from, let's say, UVW to X, Y, Z. And then what happened to our integral in the X, Y, Z coordinate? Okay, so we have an extra Jacobian factor. Okay, so we change our domain and then we change our function. Plus a factor of Jacobian. Okay, so what's the Jacobian? What is Jacobian? So Jacobian is a determinant of a matrix. So what's the matrix? Yeah, what's the matrix you're taking? You take all the partial derivative. Okay. So you arrange the, okay, so supposingly this part is called the new variable. This is the old variable. Okay, but you define your old variable using new variable. Okay, so x in terms of uv. W, Y in terms of UV, W, and Z in terms of UV. Okay. Okay. So you need to differentiate your all variable with respect to your new variable, or the codomain variable with the domain variable. So you arrange your codomain variable using the row, and then arrange your domain variable using the column. Okay. Should I use, okay, maybe I use some color to differentiate. Here is U, U, U. Okay, here is I. Let me see. X, 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 U, U, U. Correct. D1, dx, du, dy, du, dz, du. Here dz, du. Right? Huh? Correct. Wait, let me check. E? 横 Wait. I think it's correct. Correct. So, I mean, codomain stay on the row. And then the domain stay on the, wait. Let me see what's your dot. No, it's different. Okay. No. I mean, okay. So there's something going on here. Okay. What's the determinant of A, T, and A? How you compare A, T, and A? Yeah, right. I mean, what's the determinant? You know how to relate the determinant? Huh? Determinant of A is equals to determinant of AT. Okay. Yeah, so if you transpose it, it's okay. Okay. If you how about exchange row? What happened to exchange row? Different by what? The determinant. Different by negative, but we take a Jacobian absolute of Jacobian. Okay, so we remove the negativity. Okay, so if you exchange column, how? Huh? What happened to the determinant if you exchange column? Huh? Also negative, because if you transpose it, it's equivalent to you to exchange the row. Okay, yeah. So transpose the matrix doesn't change the determinant. Okay, yeah. But make sure row need to follow row, column need to follow column. If you exchange some of the term, then no one can help you already. Yeah. Okay. If you accidentally exchange row or column, make sure that the Jacobian you use is always positive. That's all. I don't think you can phrase it like that. But I mean, but you don't exchange term arbitrarily. Like X, Y, X. Okay. Yeah, if you want to exchange, you need to exchange row by row, column by column. Okay. You get what I mean? Because I can write WV instead of VW, right? Yeah. Okay. So yeah. So if you do any row operation or column operation on this matrix here, the determinant you get is differ by a minus sign. Okay. But in this theorem here, we put an absolute of the Jacobian. Okay. So in the end, you need to take an absolute of it. Okay. So that's why it's invariant on how you arrange your matrix. But the convention here is Okay, I don't know why your Knox is different from my Knox, but post out the version that I write now. Okay. So my convention here is I arrange the core domain variable in a row and then domain variable in a column. Okay. Yeah. So the node in your the one inside your node is just differ by transposing. So it's fine. Okay. Is it okay? Okay. Okay. Yeah. So keep continue. So del y over del v, del z over del v.
So we got is the original.
What?
Fine, transport and not
What do you mean?
find the original.
I also don't know which one is the original one. In mathematics, right, there's okay. I'm not sure which one is the first one that come out, but the transpose one and the normal one, they both give the same determinant. Okay. Yeah. I didn't go and find which one is the first thing people do, but this one is the first one I saw in the node. Okay, but your node seems to be different. Okay. Yeah. Okay. Okay. So okay. So remember last time what we did for this example here? Huh? The polar coordinate. We have the polar coordinate. Should we do again? Do again. Okay. I want to. You need to remember this example here. Okay. I want you to remember this example. So this is the example of changing to polar coordinate. Okay, so the domain is still the same, but we do a change of variable. Okay, so what did we do? So the variable we do is x equal to r cos theta and y equals to r sine theta. So in this case, what's our t? Okay, t is mapping from new variable to all variable. Okay, in terms of new variables. So our new variable here is r and theta. Okay, our new variable is r and theta. So here is O. Okay, this map is going from new to old. So here is equals to x and y. Okay, we define x and y to be r cos theta and r sine theta. Okay, makes sense or not? So the map is going from new to old. Okay, define all variable in terms of new variable. Okay, so here makes sense, right? Because I give you r, give you theta, you can find r cos theta and r sine theta. Okay, so this map is going from rectangular coordinate to polar coordinate. So now we want to show that the Jacobian, the absolute value of Jacobian is actually r. Okay, so how do we do this? What is j r theta? Okay, follow the definition I gave just now. This is the determinant of partial derivative of my co-domain variable with respect to my domain variable. Del r and del y del theta. Is it correct? Yeah. So I rearrange the co-domain variable in a column, then domain variable in a row. Okay. and I partial differentiate the codomain variable, the old variable, using the new variable. Okay, because I want to see, because I changed from xy to r theta, right? So I need to see how my old variable changed with respect to my new variable. Okay, that's why I put x at the top, and then xy at the top, and then r theta at the bottom. So there's another notation for this, which is this. So differentiate the old variable with respect to the new variable. Okay, so this is another notation. Okay. Yeah, differentiate all variable with respect to new variable, because we need to see how these all variable change with respect to new variable. Yeah. So don't confuse on how you put which one at the top, which one at the bottom. Okay. So in this case here, what is del x del r? What is del x del r? Cos theta. Okay, del x del theta minus r sine theta. Del y del r is sine theta, and then del y del theta is del y del theta is r cos. Okay, so in the end, what do we get? R cos square theta plus r sine square theta. Okay, all together you get r. Okay. So this is the extra, this is where the extra r coming from, which is from the Jacobian. Okay. Okay. So you can go home and try, okay, try the spherical coordinate. Spherical coordinate. So show that how this so show that how this r, what's the sign again? R square or r? Yeah, spherical. What's the extra? Okay, you get the rho square sine. Okay, so try and compute this. How this Jacobian comes out. So in this case here, do you know what's the size of this Jacobian? What's the size? 3 times 3. Okay, so this size is a 3 times 3 Jacobian. Why 3 times 3? Because you got x, y, z. Okay, in terms of rho and phi and theta. Okay. Yeah. So you got a 3 times 3 matrix, and then you need to solve it. Solve the interval determinant. Okay. Okay. So you can try this. I'll post up the solution. Okay, so let's look at some other example here. How about look at this example here? So try and evaluate this cos and sine, cos x minus 1 times sine x plus 1 dA. Okay, with a triangle. Triangle with vertex 0, 0, pi minus pi and pi pi. Okay, so we're going to use change of transformation, change of variable to solve this question here. So if you were to solve this using dx dy, right? Okay, is it doable? Both functions have xy inside them. So maybe you need to use by part or something like that. Right. Okay. So what we considering doing here is consider the transformation. U equals to x minus y and v equals to x plus y. Okay, So we make the things inside cos and sine become a single variable. Okay, so this is the new variable we're going to use. Okay, so if I make this change, this means what? My old variable x will be u plus v over 2, and y will be v minus u over 2. Okay, so we do this variable change from dx dy to du dv. Okay, so just now we say that this is our transformation from new variable to old variable. So become xy, where my xy is u plus v over 2 and v minus u over 2. Huh? You need to solve it. Okay, so if you haven't worked it out, you can test first. Okay, so x equals to u. U is x minus 2, v is x plus y. So y minus y becomes 0. X plus x becomes 2x. So divide by 2 is x. Correct? So you verify it. I mean, of course, you need to do the what's that system of linear equation, but since I already give you this, you can try and verify it. So you got u, right? U is x minus y. Okay, x minus y plus x plus y. Right, y and y cancel, but you got 2 copy of x. Divide by 2, only you get x. I mean, okay, so this equation says that the right-hand side is equal to the left-hand side. Okay, so meaning here I need to get the right-hand side, I need to get x. Okay, so u is x plus y, x minus y. V is x plus y. So altogether, how many x? 2x, 2x divided by 2 is x, so equal to the left-hand side. So this equation, how? Okay, yeah, okay. If not, you need to solve the linear equation. Yeah, so let y equals to x minus u, and then you move it here, and then find what is x. Okay, yeah, okay, good. So this is t. So if this is t, what is Jacobian? What is our Jacobian here? Okay, so remember here, what we put here is a new variable. T is from new variable to old variable defined by new variable. Okay, new variable. Okay, so what's the Jacobian here? Del x over del u, del x over del v, del y over del u, del y over del v. Okay, okay, so far, Jacobian. Okay, how about next? So what's del x over del u? Over 2. Okay, 1 over 2. And del x over del v, also 1 over 2. Del y over del u is minus half. And then del y over del v is half. Okay, so altogether, what do we get? We get half times half minus half times minus half. So together we get half. Okay, yeah, get half. All right, so what happened? So what happened here is we have changed this integral to uv, okay, to du dv. We're not sure whether the domain changed or not. Maybe let's say it changes. Okay, so cos u sine b du dv, and plus a Jacobian. Okay, absolute value of half, which is just half. Okay. Yeah. So how does this domain change? Okay, so you need to study how this domain changes. To study how the domain changed. Okay, so let's study how the domain changed. So what we can do is we can first check the boundary. What happened to the boundary? Okay, let's call this line boundary line R1, R2, and R3. Okay, and then we can label them. So let's move everything away. Okay, so far okay with this. So far okay with the Jacobian stuff. Change of variable. Okay or not? Okay or not? So far with this Jacobian change. There are two things you need to do. You need to find Jacobian. You need to find domain change. Okay. Next we will do domain change. Okay. Yeah. Okay. Let's see how this domain changes. So we can check on the boundary first. Okay. Check on the boundary. So this point is kind of weird. We pick some irrational points here. Okay. So we can check what is R1, R2, and R3. So get the lines ready. What is R1? How you describe R1? Do you know how to find the equation for R1 or not? I already give you 2 points on that line. Yeah, y equal to mx plus c. Okay. So in this case here is y equals to x. Okay. Maybe y equals to mx plus c is not so yeah. It's better to use the more general one, because if the y intercept is not given, then you don't know what is c. Yeah. So better you keep the general one in your mind also. Do you know that the y equals to ms plus c also comes from this formula here? Because your x is 0. Okay, that's why this term just become x. So this part here is the m here. Okay, the one right hand side is the m. Okay. Is it okay? Yeah. Okay, so in the first line, we got y equals to x. My y is going from 0 to pi. Okay. Pi. Yeah. How about R2? What's the line of R2? X equals to pi. Okay. So y from where to where? Minus pi to pi. Okay. How about the third line? It's kind of symmetric. So y equals to minus x. X also going from 0 to pi. Okay. Yeah. So these are 3 lines. So we need to see how these 3 lines get mapped over using our new variable here. Okay. So so which one is easier? So okay, let's look at R1 first. Okay, we'll look at them one by one. Okay, what happened to R1? On this line, what is my u? U is x minus y, but y equals to x. So my u is always 0. Okay, my u is always 0. So my u is always 0. This means this R1 here get mapped to somewhere always 0. Okay, somewhere where u is always 0. So where is u? U is this direction. V is this direction. So here. Okay, but what's the range here? What's the range? Okay, we need to check what happened to the range, right? So what is our V? V is x plus y. Okay, V is x plus y. But x equals to y equals to x, so you get 2x. Okay, so meaning your x is in between 0 and pi. So your range for V is from 0 to 2 pi. Okay, so you get your range here for V. For U, what happened? U is always 0. Okay, so U is always 0. But your range is determined by your v. So v is from 0 to 2 pi. So you cut at 0 to 2 pi. Does it make sense? So this is the new R1. Okay or not? Okay, homie. Okay. Yeah. So this is the u equals 0 line. Okay. V is going from 0 to 2 pi. Okay. So far, okay. Okay or not? Hello? Okay. Okay. First line. Any question or not? Okay. Okay, I understand. Okay. All right, next. How about next? Yeah, use this. So how about next? X equals to pi. Okay, what happened to our u? And what happened to our v? What happened to our u and v? So, yeah, so what happened to our u and v? So x equals, u equals to what? Pi minus y. Okay, v equals to pi plus y. Okay, but there's a y here. We don't want y anymore. So if you combine them together, I think you should get u plus v over 2 equals to pi. Okay, or you can straight away use this one. Okay, you can straight away use this. There's a relation between x and uv. Okay, so you just sub your pi into x. Then you also will get this. Is that okay? Okay, so in this case here, this is convenient. What is this? What is u plus v equals to 2 pi? What is this? Huh? This is a line, right? This is a line. U equals to minus v plus 2 pi. Correct? Correct. Okay, so what's this line here? U equals to minus v. Okay, u equals to minus v is this line. But you shifted up by 2 pi. Okay, you shifted up by 2 pi. Okay, you shifted up by 2 pi. So what's the range? What's the range here? What's the range? What's the range? You know what's the range is? So you got the, wait, let me write properly. So u equals to minus v plus 2 pi. Okay, so you got u equals to minus v and then shifted up by 2 pi. So what's the range? How you determine this range? Okay, so your one of the endpoint is y equals to minus pi. The other endpoint is y equals to pi. Okay, so in these two 2 point here, what is your u and v? When y equals to minus pi, your u is what? Here, use the first one. U is 2 pi. Your v is 0. Okay. How about when y is pi, your u is 0, v is 2 pi. Okay. So when y equals to minus pi, it corresponds to 2 pi 0. So here. Okay. When y is pi, 0, 2 pi correspond to a point here. Make sense? Okay. So this is the endpoint. Okay. And then what's going on? Let me see. So pi minus pi, where is it? So let me plot this point here. So this is the pi minus pi. Okay, pi minus pi got sent to 2 pi 0. So which is here. Okay, let's plot the other angle, the other point. Pi pi. Okay, pi pi got sent to 0, 2 pi. So which is here. So my direction is going upward. Okay. Okay, so you can see that this line here get mapped to here. Okay, my direction wrong. So let me. Okay, so this line here get mapped to here. Is it okay? So we identify this point to this point, this point to this. Okay. So far, so good. Qingrou got question or not Qingrou? Okay. Can follow. Okay. Okay, next. Okay, next R3. Okay, R3, you do similar stuff. Okay, what do you do? Okay, you do similar stuff. U equals to U equals to x minus y, which means it is 2x. V equals to x plus y, y equals to minus x, which means it is 0. Okay, so this map to V equals 0. Okay, is it okay? Okay, okay. So this is a V equals to 0 line. Okay, but how we find the range? How do we find the range? How do we control U? Okay, U controlled by 2x. Okay, but x is controlled in term by this range here. Okay, so this implies what is my U? What happened to my U? 0 to 2 pi. Okay, so from 0 to 2 pi. So this line get mapped to V equals 0 and then cut from 0 to 2 pi. Make sense? Okay, so all together we get this triangle here. So here is a new R2, here is a new R3. Okay, here's a new R3. Okay, yeah. So what happened to the middle point? How do you decide a middle point? Yeah, good. I mean, this is the whole region you need to integrate. So now we only determine the boundary gets sent to the boundary. Right? So how about the middle one? What does the transformation changes does to this line? Right? Stretches. Yeah, stretches. So in principle, how you do it? Okay, you don't need to do it. I just explain to you. Okay, what you need to do, you just check the boundary. Okay, so what happened to this middle line? You can imagine you have this R2, right? Okay, so you also can form a lot of straight line here with the endpoint bounded by these two lines, correct? So in principle, you can check for all these lines that get mapped to this line here. Okay, so in principle, I mean, you can write down infinitely many lines here, correct? Correct. Okay, so if you do this check using the change of variable, you should get all these lines. Okay, but now we just reduce it to checking the endpoint of this line and one of the line. Make sense or not? Okay, yeah. And also, yeah. Hmm. Also, it's not possible for this line to get sent outside because this is a one-to-one map. You can't do that because if you make it outside, right? Make it outside of this boundary, then it will be infinite. But this is not infinite. I mean, cannot say this is not infinite. I mean, it won't be one-to-one. Okay, so that's why you have to stay inside the boundary. Okay, but for the purpose of this course, I think you just need to check the boundary. Okay, you just check the boundary. Huh? How to check the boundary? Then this is what we did. So you have this domain, you get the boundary, and then you see where the boundary mapped to. Yeah. Yes. Huh? Yeah, let's do one more. Let's do one more question. Okay, this is counted hard question. Okay. Yeah, there are two things you need to do. Hmm. Hmm. Huh? Oh, we haven't compute the integral yet, right? Okay. Yeah. Yeah. Excited to go to another example. Okay. So how to do the integral? Okay, how to do the integral? Okay. Okay. So we already determined the Jacobian. Okay, already determined the domain change, right? Okay. So now we need to do the integral. So how to do the integral? Same thing. So where's my integral just now? So let's bring my integral up. Okay, so this is my integral here. Okay, so now it's a du dv. So how you make into du dv? Do you have any idea? Okay, so we do the double integral. Okay, so the order I fix is du and dv. So if I fix du dv, right? Okay, so I need to fix my v first. I need to get my v first. So my v is bounded by what? 0 to 2 pi. Okay, if I fix my v from 0 to 2 pi, okay, what happened to my y? U. What happened to my u? Okay, you can see that this u changes at every v. So how does u changes? Is bounded below and bounded above by what? Bounded above, bounded below by 0. Okay, but bounded above by what? What's this line here? We already determined this line. Negative v plus 2. Okay, good. Yeah, so this is the range you need to integrate. Okay. Yeah. What? So cannot be plus 2 times.
Please complete next semester.
Okay, so we solve this integral here. Okay, do you want to try and solve this integral? Okay, do together. Sure, let's do together. Okay, so we first integrate with respect to u first. Okay, so with respect to u. So respect to u. Okay. Okay, we cannot split into product, right? Because our integral domain here depend on v, so you cannot just straight away split. Okay, so you need to finish your u first. So integrate with respect to u, what do you get? Sine u, sine v. Okay, sine u, sine v. From 0 to 2 pi minus v. Okay, note that I pull my half outside already. This is a scalar I pulled out. dv. Okay, so this is dv. Okay, so what is it? So you get sine v sine 2 pi minus v dv. The other term is 0, so we don't care. What is sine 2 pi minus v? Anyone know? You shifted the sign with 2 pi. and sine is even. Okay, you shifted 2 pi, you don't do anything because sine shifted 2 pi is the same sign. Okay, but sine minus v is what? Is minus sine v because sine is even. So you get minus sine v. Okay, if you like, I write down sine 2 pi minus v.
So you still need to.
What do you mean? What do you mean?
I need to change for the I negative b to negative sine b.
You don't want to change also can, but you need to integrate from here. If I change it, then I can combine my sine v. Okay. Okay. So this is equal to sine minus v, which is equal to minus sine v. Okay. Yeah. So so what do you do here? You got sine square. So you reach your favorite double angle formula. Yeah. Okay. So this is a half of 0 to 2 pi of cos 2v over minus 1 over 2. I think I taken account of this minus already, right? Okay, yeah. Check what's the formula? Correct. 2 sine square v equals to 1 minus cos 2v, is it? Yeah. Yeah. Okay. Formula here. Is it correct, this formula? Yeah. Okay. So continue. You continue with this. Continue with this integral and half time minus 2 pi, which is minus pi over 2. Okay, maybe we take a break and then we do one more, few more, or one more exercise. One more very important exercise. Exam got similar type.
So why the answer is the negative one? The area is negative.
Yeah, kind of.
And if you got negative one,
Last time, remember what we said? If the orientation is below, then we'll get negative. But what's this shape? It's very hard to see. I'm also not sure. Maybe it lies below. I mean, there's more things below the z-axis because cos and sine are also cannot differentiate quickly. Yeah. Mm. Yeah, take a breath until.这个是那个我们一开始的那个，
我一个然后出分，
然后这边找这边正点，就是这个。
等一下，可以再
我怕 variable 过后多出这个，哦，这个新的 variable。对对对Jacobian，对，我们一开始穿的这个。啊，
等一下，他们没有来给我称喝一下，
蹭车。哦，
对吧？
对啊，
因为
中汉都没有来。
我们没有来，没看到没？
我知道，中汉没有来。
我其实不知道我昨晚的，我应该是最持续那个哦。哇，看到你眼了
啊？
看到你有点烦的。
哦，你看，
没别。
翁真庸0，OK，我知道。OK，good，看到了，Thank you。靠北也，方舟也。 江宏宇、李杰、李培、李培、李玉章、连叶、林天阳和刘佳琪，don't have 刘品义，okay. 刘夏红，okay. 龙凌波 I think not 这组凌波啊，不懂啊，hostel 彭香瑜，彭玉玲，施杰生，don't have 宋景华，don't have 宋子飞，王培武。王西龙，王宇轩，吴俊宇，OK，谢宇轩，徐子凯，杨景荣 here，所有，张云，张云呢？喂，张云，not here，赵静涵，OK，right，赵以轩，周子康 here，洪嘉轩 not here，here report。Daniel Berwin Ding not here. Chia Ming, I think I saw Chia Ming. Okay, Chia Ming. Xu Long not here. Pei Yu, Song Hao, Yi Xun, Jie Seng, Wang Tian, Ming Hai, Wen Yao, Leong, okay, Leong here. Wen Yao also, okay. Hun Tat, Yi Hui got Yi Sun. 洪明、嘉盛、Reynis、Wen Keng 到 here， 魏涛，OK， 魏涛，轻柔、一招、所以热真，OK， 冲开界，OK， 王雅美 ，OK， 有 ，OK，sorry， 盛豪 ，OK。苏泽辉 ，OK， 托 here， 真有福语，吴承泽，
这个前面的东西是什么？
这个是那个 Jacobian 那个 change of variable， 你刚才没有来用这个，如果你要换 variable 的话，会多出这个东西啊。
会多付这一块钱，
然后这个东西就是这个我们送的那个 Jacobian，
所以这个东西是
对，
就是这两个里面的东西 x 和 y
不是这个东西是你的这个 change of variable 算出来的，就是你的这个 map， 这个 change of variable 的 map， 然后你要算它的 partial derivative，
这个两边啊 u 减 x 减 y， 然后变成 x，
就是你决定的呀，
我决定这个，
你要决定这两个东西。
OK， 我可以让我的 u 等于 x 减 y 跟 v 等于 x 减 y，
对，
可是我
这个直觉是这样。
OK， 只是我将把它变成 x 等于 u 加 v 这个是这样来的，
这个组合，现在可以拿出来 solve 那个 system of linear equation。x 等于 u 加 y 吗
？x 等于 u 加 y，
对 ，and then 你可以 sub y，
就把这个东西丢进来，
然
后我这个一样这里把
组合，
然后再把这个丢进来，
一样，
然后再把它丢回进来，然后这
，yeah，
所以我还是要去做这个东西，去拿到这个 constant 出来。
现在要去做这个东西，
就是我要做好这个东西。
你没有这个东西，你做不出这个东西，因为这个东西是用这个东西。
对，就是说我做好这个东西，
然
后把它带进来这边，我去拿这个 constant， 然后我去换牵手 variable u 跟 v 的时候，我就可以把这个 constant 丢进来。
对，
就
相当于其实我不一定是 constant 来的，它可能是其他东西。
就是一个东西啊，就可能
只要我 change of variable， 我就一定会有一个 Jacobian 出来。
对，没有错，
就是为了要弥补那个差距。
对，它那个
Jacobian 它正负性不确定是我知道没考虑。
你放它进去之前，你把它变成正，还是不？
我是哪个地？ 的话，它得到什么定义？
那时候根本考试不会出这样negative题。
考试是不会
正
常的那个
正常的话，
定义是什么？
可能你要留住那个
你应该要留住那一个空，然后这样子的一个方向，把它变成，只是说如果是
它是
negative，
你要
自己
加一个什么？那基本的话，积分integral 就是要分成两段。
对，减的那一份你要加一个减，对，就是 modulus 的定义。
那考试时候应该不会出现这种Jacobian。
对。negative 的话，我建议 modulus 掉。
那个你讲 Jacobian 讲的这个不是？
对，但是有时候它的 Jacobian 出现 function 嘛，这样你就变成 modulus 一个 function 了。
会吗？
可以，但是就是那时候的话，你就要把你的 function 分成 positive 跟 negative，因为 modulus function 的 definition 是 x 单 x positive negative x， 所以不会出来这样复杂。
考的时候不会出现。
OK 啦，可以啦，
但是理论是这样。
然后这个就是你刚刚说这个之后要讲的，就考试出现是哪道题？
等一下我要讲，
等一下，能信吗？就是
这个，
就这道题是吧？
类似的会出现。
然后就是考试就是他那个题型是不是跟就是下周那 quiz 基本是一样的？
是，
对啊，
没错。Okay, so I think you want to pay attention to this question here because there will be similar stuff coming out. This change of variable. Cannot talk too much later. Come on. Okay. Kidding. Okay. So change of variable of this function. Okay, so you got e to the x plus y, x minus y. Can you do different integration with respect to x, y or no for this function? Do you think it's easy to do? U equal to x plus y? Sure. Now what skill do you mean? Oh, you can swap. Just the diagram swap. Okay, just the diagram swap. Okay, just the diagram swap. Okay, you can swap, but just the diagram will swap. Okay, for example, if you want to let your new variable u equals to x plus y, v equals to x minus y, but today your mood is not good, you say v equals to x plus y, u equals to x minus y. You just swap the diagram. Yeah. Compared to the previous one. Okay, the two diagram will swap. How to swap? I think it's a reflection. I think it's reflection on this line, I guess. Rotation. I feel like it's reflection, but you can test it out. Yeah, U and V swap. U and V swap, I think is reflection. Huh? Yeah. I mean this two diagrams swap, but don't care. I don't care about this diagram first. But what I mean is, if you swap it, then you will. I think what you do is swap with a UV line. You can try. Okay, but that's not our point today. So our point today is how to do change of transformation for this integral here. Okay, and then this R here is a trapezoidal region with 1, 0, 2, 0, 0, minus 2, and 0, minus 1. Okay, so first you plot this region first. Okay, so where is this 4 points on xy plane? Okay, these 4 points, 2 of them are on the y-axis, 2 of them on the x-axis. Okay, so this is the shape you will get. Okay, so you get 1, 0, 2, 0, 0, minus 2, and 0, minus 1. Okay, so you combine this, you get a trapezoidal region. Okay, so this is the XY plane. So let me do some label here. This is XY plane. Okay, so the transformation of variable I chose here is the change of variable I pick here is u equals to x plus y, v equals to x minus y. Okay, this is the one I pick. So in this case here, actually we have a similar transformation. So this is just same. This is the same as before. And of course, okay, let's write down the t first. T is going from new variable to old variable, where x is equals to u plus v over 2 and y is equals to u minus v over 2. So you can see that this t here, right? You see, this t is going from new stuff to old stuff. Okay, although our integral change from old to new, all right, but this transformation is going from new to old. So this is the thing you need to take note. Okay, transformation is going from new variable to old variable. Okay, so what's our JUV? Okay, our JUV is, yeah, 1 over 2. So the formula is del x over del u, del x over del v, del y over del u, and del y over del v. So all together is the same calculation just now because we use the same change of variable, which is 1 over 2. Yeah, my note, no problem. Okay, 1 over 2. Okay, so the next thing, you already found your Jacobian. Okay, the next thing is you determine the domain change. Okay, need to determine the domain change. How does your domain change? Okay. Yeah, so how does your domain change here? Okay, so we just check the boundary. Okay, we just check the boundary. So how many boundary here? R1, R2, R3, and R4. Okay, so there are 4 boundaries. So you need to list all the 4 boundaries. R1, R2, R3, R4. So what's the R1 line? Wait, don't look at the picture. Don't look at the picture. So where are we now? So we are on the XY plane. Okay, we are on the XY plane. Okay, we are on the XY plane. So the point here is why this picture upside down is because how we define the t. Okay, the transformation, the Jacobian of the transformation is going from new variable to old variable. Okay, yeah, but this is 1 to 1, so we can go from old to new. Okay, so what is R1? R1, what is R1 line here? R1 is a horizontal line. Y equals to 0 for x from 1 to 2. Okay. How about R2? Okay, the line is given here, but do you know how to find this? Yeah, this is given, but do you know how to find it? Same also. Okay, use the line equation because you are given 2 lines here. Okay, so you get x minus y equals 2 for what's the range here? So from, yep. Say again. No. So this is the XY plane. This is the XY plane. This is what we started. Yeah. Yeah. So now you don't know about this. You know nothing about this. You don't know about this yet. Yeah.
You know nothing about this yet. Okay, what we know is only this trapezoidal region. Okay, the only thing we know is about this. We don't know why we get this yet. Okay, these pictures, let me stay here first. Later we'll explain. Okay, so we get the second line. What's the third line? Third line is x equals 0 for y from -2 to 1, -1. Okay, correct. Yeah. How about R4? Okay, you got 2 points here. Okay, use this 2 points to compute the line equation. Okay, and then you will get x minus y from -1, sorry, 0 minus 1 to this one, get over it, to the 1 0 1 0. Okay, yeah. Okay, okay. So I skip how you find this line equation. You need to know how to find it. So given 2 points, use the line formula, equation of line. Okay, so you need to check where does these 4 lines go. Okay, let's say we don't know what's the top picture yet. Okay, how to change variable? So so y equals to 0, right? Okay, so we know that y is also equals to u minus v over 2. Correct or not? Okay, this implies that 0 equals to u minus v, which implies that u equals to v. Okay, so this one becomes u equals to v. So if it is u equals to v, what happened to the endpoint? Okay, where is u equals to v? So this is a uv plane. Okay, so now we get this map here, uv plane. Okay, u equals to v is this line here. Okay, but how long we should take? Okay, this depends on the range of x. Okay, depend on the range of x. So we need to check when x is 1, what happened to our uv? When x is 1, what is uv? U is 1, v is 1. How about x is 2? U is 2. Wait. 2 plus 2. U is, wait. Yeah, u equals to v. Okay, so let's write it down so don't confuse myself. So u is x plus y. So x is 1, y is 0, so you get 1. Okay, this is correct. Similarly, v is equals to x minus y, which is 1 minus 0, which is 1. Okay, u is x plus y is equals to 2 plus 0, which is 2. V is equals to x minus y, which is 2 minus 0, which is also 2. Okay, so at one endpoint, so let's plot the endpoint out. What do you mean? If I know u equals to 1, v equals to 1, yeah, you can. You also can do that. Yeah, you also can do that. Yeah, you also can do that. Yes, you can do that. Okay. Yeah, so let's plot this point. This is green. This one. And another one. Okay, red. All right, so where is 1 0? Okay, 1 0 is the purple one. Okay, so the purple vertex 1 0 gets sent to 1 1. Okay, so here is 1 1. Okay, how about 2 0? Okay, 2 0 is the blue one. Okay, the blue one gets sent to 2 2. Okay, so 2 2 is here. 2 1. Okay, so we cut our y equals to v from 1 1 to 2 2. Okay, make sense? Okay, so we get this line now. Okay, imagine you don't know this here. Okay, we got this line. Make sense? Okay. Okay, so how about next line? Y minus x minus y equals to 2. So what happened to our u and v? So you can see that y equals y. Okay, so you can see that. Okay, so let me write down. So v is equal to x minus y, but x minus y is 2. So it's become v equals to 2. Okay, you get the v equals to 2 line. But v equals to 2 line is a horizontal line. But where do you cut it? So you need to check the endpoint again. Okay, you need to check the endpoint, where the endpoints go. So how to check it? Since the v is always 2, right? You just need to compute what is w. Okay, what's w? What is u? Sorry, what is u? Somehow come out a new variable. What is u? What is u? Okay, so what is u? So at xy equals to 2, 0, what is u? U is what? U is x plus y. So in this case, you get 2, 2, 2, right? 2 plus 0. 2 plus 0, you get 2. Okay? So you need to check what happened to these two endpoints, right? Okay. So when xy equals to 2, 0, what happened to my new point? Okay. We know that the v is always 2, but what happened to u? Okay. U is equals to x plus v. This is the change of variable we make just now. U is equal to x plus v. Okay. So 2 plus 0 is 2. Okay. So in this case here, so in this case, 2, 0 gets sent to 2, 2. Is it okay? Following or not? Following? Hello? 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 Okay, can follow? Okay, how about at the other endpoint? When xy equals to 0 minus 2, what happened to my u? Negative 2. Okay, good. So u become negative 2 plus 0, which is negative 2. Okay, so this point here gets sent to 0 minus 2 gets sent to negative 2, 2. Yes. Okay, so let's plot these 2 points. So we can check here 2, 0 gets sent to 2, 2. This is coincide with what we did just now. Okay. How about 0 minus 2? 0 minus 2 is this red one. So get sent to minus 2, 2. So here. So this is the red point. New red point. Okay. And then v equals to 2. Where is v equals to 2? Okay. So this line is the v equals to 2 line. Okay. Cut at the point minus 2, 2 and 2, 2. Okay. So far, okay. Okay. Yep. All right. So how about next? Continue. Continue. Okay, you can see that this is the part of mathematics, right? Okay. Although we are dealing with geometry, but you see, what we do here is all algebra. Okay, we do algebra, do algebra, do algebra. And then we go back to geometry. Okay, and then we do algebra, do algebra, do algebra. And then we go back to geometry. But when you do algebra, right, don't lose inside the sea of algebra, okay? What I mean is, don't confuse when you do this calculation. So always keep in your mind what you are doing. Okay, what is the endpoint? What's the line you get sent to before? Okay, because sometimes if you dive into this algebra, right, you will easily get lost. You get what I mean? Yeah, you tend to make mistake. That's what I want to say. Okay, so what is x equals 0? Okay, the line gets sent to where? When x equals 0, we have one change of variable, right? U plus v over 2. Okay, this implies that 0 is u plus v over 2, which means u equals to minus v. Okay, u equals to minus v. So how about the endpoint? What about the endpoint? U equals to minus v. How to find the endpoint? So you need to find at y equals to minus 2, what happened to our uv? U is x plus y, v is x minus y. Okay, correct. So at y minus 2, what happened to our x and y? X is just 0 and y is minus 2. Huh? So uv is just minus 2 and 2. Where you get minus 2 and 2 at y equals to minus 2. Actually, you have an extra condition, right, at the beginning. X equals 0. Because it lies on the line of y minus x equals 0. Make sense? Make sense or not? We start with the line x equals 0. Okay. How about the other endpoint? The other endpoint is y equals to minus 1. Okay. So u is equals to negative 1. V is equals to 1. Okay. Good. So you see that 0 minus 2 gets sent to minus 2, 2. Okay, this is the same calculation we did just now. Okay, it's equal. I mean, the answer is equal. This is good. That means they connect. Okay, 0 to minus 1 gets sent to minus 1, 1. Okay, so where is 0 minus 1? So it's this green vertex here gets sent to minus 1, 1. So which is this point here. And what's the line that connect these 2 points? You remember or not? What's that line we computed just now? Y equals to negative x. Okay, so this point here is y equals to negative v. Okay, negative v. Yeah, u equals to negative v. Right, this is the line we have. So this is the line that connects the 2 new points here. So let me write something. So here is minus 2, 2, here is minus 1. Okay. So how about I write everything out? 2 gets sent to this point. The point 0 minus 1 gets sent to the other point. Yeah, I mean, to be precise, right, you can name this vertex, name them with different name. 1, 1 to 1, 1, 2, 2 to 2, 2. Yeah, you can give different name. But I want to get the idea first. Okay. So we already get these 3 lines here. Okay. How about the last line? How about the last line? Okay. X minus y equals to 1. So this implies that v is equals to 1. Okay, because v equals to x minus 1, which is 1. All right. So at the end point, what happened to our new uv? Okay, at the point 0 minus 1, what is our u? Minus 1. Correct. V is 1. Okay, minus 1. At the other end point, what do you get? 1 and 1. Okay, so let's check again. So we see that this R4 here, where is R4? R4 is this part here. It gets sent to V equals to 1. Okay. And then the two endpoint is minus 1, 1 and 1, 1. Okay, minus 1, 1 and 1, 1. So all together you will get another trapezoidal region in UV. Okay. Where? Bottom. This one. Okay, so we can write everything out. So this point gets sent to a new point, minus 1, 1. And the other one gets sent to a new point, 1, 1. Okay. Yeah. Okay, so one last thing you have to do. You have to compute the integral. No, I mean when you do right, you don't need to explain like me. You just keep doing. All right. You no need to explain like me. You just keep doing. Okay, so this one you determine the domain already. This one 20. No, no. Definitely more marks. I don't know. Forgot. Yeah.
这样的这题我为什么不用做？
先啊，如果那个其他的也将重要。
Don't know.
有点一不到位，保持不到位。
Yeah, this one very important. Very. Definitely important. And then what I don't know. This one very important. Okay, so let's compute this. So we want to compute this, right? Okay, so we change variable to u and v. Okay, we change variable to u and v. U over v of du dv. Any Jacobian or not? Just now we get. Huh? The Jacobian is 1 over 2. So how this do you know how to compute this double integral or not? Du dv. Should be okay. Should be okay. Okay. So I pick u and v. So my direction is u and v. So I need to fix my v and fix my u first. And then fix my v first and then fix my u. So my v is going from where to where? Huh? My v is going from 1 to 2. Okay, my v is going from 1 to 2. How about my u? So you need to see every v, what happened to my u? Right, you can see that when my v go from the top to bottom, my u getting smaller and smaller and smaller. So how do I control the u in this case? How do I control? V and negative v. Okay, bounded below by negative v, bounded above by v. So here we got 1 to 2 minus v to v of the whole thing here. Okay, good. Okay, so how to integrate this? How to integrate this? Can you do integration or not? How to integrate e to the u over v with respect to u? What do you get? Multiply or divide? Okay, divide by 1 over v, which is multiplied by v. Okay. So half v e u over v from minus v to v. d dv. Yeah. Jacobian is negative 1 over 2. Okay, good. Jacobian is negative 1 over 2. Yeah, but you need to put absolute, correct? So when you put inside this yeah, when you put inside the integral, you need to put absolute. Okay. Yeah. Right. Good. Hey, does it mean just now we compute wrong or correct? Never mind. Okay. Huh? No. Here I think we compute wrong. No. Here. Absolute value is when you put inside the integral. Yeah. When you put inside the integral, you need the absolute value. Yeah. The formula here, C. So the formula we write just now, right? Okay. This Jacobian here, where's my? Yeah. So this is the absolute value. It's not the determinant. Jacobian itself is the determinant. Okay. Over the determinant, you still need an absolute value inside the formula. Okay. Make sense or not? Okay. So you got this double line for determinant and then this double line for absolute. Okay, absolute on the Jacobian. Okay. Is it okay? So everything placed inside the integral. I mean the Jacobian placed inside the integral should be positive. Huh? Yeah, you can. Yeah, you can. What? 30, what happened? Yeah. Okay. So right. Where is it? Too tedious explaining the domain. Okay. Okay, continue. Anyone finish compute this? Anyone finish computing this? E minus E minus 1 dv, and then E minus E minus 1 over 2 or V square over 2 from 1 to 2. So you get 3 over 4 E minus E to the minus 1. Okay, so you get this. Okay. Hey, what if I change order? If I change dv du, what happens? Huh? Can or not? dv du. Yeah, so you need to do 3 parts, right? Because you can see that if I cut at minus 1, 1, and 1, 1, okay? If I cut at, I mean, u equals to minus 1 and u equals to 1, you can see that the top and bottom controlled by different number, different graph. Yeah. Okay, so you might need to cut into. Triple, you will cry, only. No, the boundary become a surface already. Yeah. I mean, you can draw the domain, right? You can draw box, draw spherical, draw sphere, draw cylinder. But then the boundary become a surface already. Okay, the boundary becomes a surface. Maybe not for this type of arbitrary change of domain, but you can see example there's some example here. So for example, this one, this is the usual one. Just now I asked you to do exercise on. And then this one also easy. Just easy one. Yeah, I tell you it's easy first. Then I'll show you the answer. Okay. Or you want to do it together? Or you want to go vector calculus? You want to do do what? Do? Okay, let's do it. Maybe vector calculus next week. Next week we got 6 hours. Huh? Oh, okay. The last one you got 3/4 e minus e to the minus 1. Okay, let's do one. Okay, let's see how this change of variable work for three variable case. 3 to 6 Friday. Huh? After I book the venue, then I'll post it. After I book. Yeah, after I book the venue. I haven't confirmed. Yeah. Definitely. After I book the venue, I will tell you guys. 1.5 my target. Because ODE just need half week. Because only 15 slides, I think. No lecture, I guess. Next week holiday. 1 day holiday. 1 day holiday. Yeah. I mean, depend on if you guys want extra class, then maybe you can arrange. Huh? What? The mock test is the quiz. Yeah. What do you mean by not discuss? Oh, we can discuss the quiz inside the class. We can. I think enough. I hope enough. Yeah, I hope enough. If you want, we can open extra class. Go to my graduation is Saturday. I mean, I go Saturday. So if you want to do weekdays, you can. Yeah, later we decide. We can decide. If the worst case, maybe we do Friday again. Worst case. Hey, cannot Friday. I got meeting. Okay, we will decide again. Next week we decide. Okay, try this example here. So how to find volume bounded by ellipsoid? Okay, so how to find this using change of variable? Okay, so first note that these A, B, C, right? Okay, are all positive. Okay. So what we can do is we transform this to a sphere. Okay, we transform this to a sphere. Why? Because if we transform it to a sphere, then sphere, we know the volume of sphere. We know the formula for volume of sphere. Okay. Okay, let's see what do I mean by that. Yeah, let's see what do I mean by that. So what I'm going to do is consider the following changes. U equals to X over A, V equals to Y over B, and W equals to Z over C. Okay. So in this case here, what happened to my equation? My equation become Y squared plus V squared plus W squared equals to 1. So this is the sphere equation, right? So volume of sphere, you know, right? So you will integrate over the spherical coordinate on the function 1. Right? So triple integral, if you do triple integral on function 1, you get the volume of the domain. If you do double integral on function 1, you get the area of the domain. Okay. So if you want volume, you can do triple integral on the function 1. Okay, so what's the Jacobian here? So this Jacobian is what size? 3 times 3. Okay, so this Jacobian is a 3 times 3 size. But you will realize that actually a lot of term in this Jacobian is actually 0. Do you see why? Do you see why? Okay, I mean, because your variable only defined using one variable, okay, in terms of one variable. So the other variable doesn't affect the others, right? So let me write down what's the thing we need to compute here. So we have dx, du, dx, dv, and dx, dw, and then dy, du, dy, dv, dy, dw, du, wait, sorry, dz, du, dz, dv, and dz, dw. Okay? All right. So you see that x only defined on u. Okay? So there's no other other variables such as v and w. So if you partially differentiate it with respect to v and w, you just get 0. Okay? So, okay, maybe let's write another set. Maybe it's easier to see. X equals to AU, Y equals to BV, and then Z equals to CW. Okay. Okay, so what do you think you get here? Dx du, what do you get? A, dx dv, 0, dx dw, 0, dy du, 0, dy dv, b, dy dw, 0, dv du, dv dz dv, 0, dz dw, c. Okay, so you can see that you get a diagonal matrix here. So what's the determinant of a diagonal matrix? Product of the diagonal. Okay, so it's ABC. So since ABC is always positive, right? We assume just now. So this is always positive. Okay, so what is going on here? So we have originally x, y, z, okay, which is x squared, a squared, plus y squared, b squared, plus z squared over c squared, that's equal to 1. Okay, we change this to u, v, w. Okay, we change this to u, v, w, we call it x. This is a unique sphere. Or because we need the volume, so we calculate the actually the solid sphere, which is a ball. Okay. Yeah, so we want to calculate the volume of the ellipsoid, which is integrate over R on function 1, right? So your domain is an ellipsoid, and then you triple integrate on function 1, you get the volume of the domain. Correct or not? You reduce one level down. Okay. Remember the property? Do you still remember a property last time? When you triple integrate a function 1, you get the volume of the domain. Yeah. Right? So you reduce one level down. Okay, so what's this? So after you change your variable, it becomes what? It becomes integrate over du, dv, dw. Okay. What's the Jacobian here? ABC. Okay, you got ABC here. But ABC are just constant. Okay, ABC are just constant. So you can pull the ABC out again. So ABC is just constant. But you are integrating over a unit ball with function 1. So what's this? This is actually a volume of sphere. Volume of sphere. So let me put Vx. So what's the volume of sphere in this case? No. 4/3 pi r cube. Okay, 4/3 pi r cube. But what's the unit of the sphere? But what's the radius of the sphere? 1. So 1 cube. So you get 4/3 ABC pi. So what does this mean? This means that if you consider the volume of ellipsoid, the volume is differ by ABC from the unit sphere. Okay. Yeah. So you can see that this domain change here, right? Actually not big, not kind of a domain change we look for just now. This domain change is easier. Okay. But in general, if you, I mean, it's harder to determine the surface, how the surface change. Yeah, kind of. Yeah, kind of. No lah, we won't go to 3D domain change. We won't go to 3D. This is too hard.
You know it's maximum already.
Just now the one, yeah. Just now the one. This one still okay, but just now the one, this one. Yeah. This one. Very important. Yeah, very, very important. Very important. Very important. Okay, can I ask more? I mean, this is the correct answer. 100. Cannot. Okay. Yeah, we got 4 minutes left. So I mean, he. Five or six, I forgot. Huh? 5 or 6, yeah.
Why more than?
You sure? Oh, I mean, they just combine it. Yeah, they just combine it. Yeah, chapter 14 until until the end, ODE. Yeah. Also the quiz, right? Quiz is on 14 and 15, so until today. And multiple integral and partial derivative until today. Yeah, until today. So next Wednesday, what time? 9 a.m. to Thursday prime 5 p.m. Okay, more than a day. So you can sleep well and then wake up at 2 again. Final, yeah, four. ODE, vector calculus, multiple integral, partial derivative. And final, this is final. Midterm, partial derivative and multiple integral up to today. Yeah, up to today. What? Which one? Which one? Final, everything after midterm. Up to ODE. Yeah, ordinary differential equation.
Wait.
Don't have. Oh yeah, that one don't have. That one don't have. Yeah. Partial, huh? Midterm. Oh, okay. Okay. Partial, and then partial derivative, multiple integral, vector calculus, ODE for final. Yes.
What do you mean? I haven't followed out the previous year. Yes.
哦，这还没有上门，
没有。
哎呦，他这一张啊，主要是一个两次考，然后这个 OK，这个 OK，就是那个欧了，哦，没有。机会死掉，
Any other question, concept question, or quiz or assignment? And not assignment. We can. What do you mean? Oh yeah. Hey, Fangzhou here, right? How? Okay. Who else? Just now I couldn't call you. Who are you? Your name? Jason. Lý sao? Okay.
我前面一定也是有错啊，我你说老师班级。
是杰森。Okay, if not, we start next week better confidence. Okay, see you next week.
Có 没有 pause 呢？有 pause？